Okay, so this being the first course, please do not hesitate to ask your questions, because what the succeeding speakers will do will depend on material in this. Okay. So I have arranged my slides according to my 6 lectures. And so I have provided a list of slides for each lecture. Lecture 1, 2, 3, 4, 5, 6. And there's some extra material which I'll try to fit. I don't know where it will fit, but it's very important material. So this is so that when you study, you can go back to the list of slides and quickly review what I understood, not understood. Also for you to ask questions, this is convenient. You can ask on slide number so and so, statement number so and so. It's very easy. So let's begin with the first slide. So I take it that all of you have had some exposure to algebraic geometry, like some basic textbooks like say Hartshorne kind of books. You are unafraid of turning pages and looking for a result somewhere in that book. Doesn't mean you have to know everything by yourself with no book near you. But you should be able to look at the book and turn pages, look at the index, find out something that you want there. So this ability with something like Hartshorne's book, another book is Mumford's Algebraic Geometry 2, I think it is called. And there are some other books, nice books. And I am too old to know the modern nice books, but you must be knowing. And so you will have to consult them time to time as you go through this perhaps. Then go consult. Always take the opportunity of going down, down, down till you know the proof fully. But don't let it paralyze you from taking the next step. So you have to do a balance between digging and understanding why this happens, and also understanding its place in the overall scheme of things. Okay, so we are fixing an arbitrary base field. The reason I emphasize arbitrary base field is I am not assuming K is algebraically closed, or I am not assuming its characteristic 0, I am not assuming it's perfect, nothing at the moment. At some crucial moments, some more things may be needed. And the spaces that we are going to deal with are called algebraic schemes. And I take it you have seen what's an algebraic scheme, because the most basic thing which all of us study in our first course of commutative algebra is a finite type algebra over K. Finite type. Which means there is a homomorphism of rings like this, and there are some finitely many generators such that every element of A can be written as a polynomial in those. But that doesn't mean A is a polynomial ring, it only means A is a quotient of a polynomial ring in finitely many variables. That is what is a finite type K algebra. And you always study these things. There are very nice theorems which apply to this. For example, Noether normalization kind of theorems. Hilbert basis theorem tells you this is Noetherian. They apply in this situation. And then for homomorphisms, you take things of this kind. This is a K homomorphism. So if we only studied this, that will be the affine analog of algebraic schemes. An algebraic scheme has an open cover by open subschemes, each of which is isomorphic to some spec A, where A is a finite type K algebra. And a morphism between such algebraic K schemes means, in algebraic terms, you can take an affine open cover of the codomain by such things and take its inverse image, and inside that refine it by an affine open cover of the domain, and then you will get lots of maps between spec AI to spec BJ, or spec AIJ to spec BJ if you want to write a lot of indices, and they will be of this kind, induced by this kind of homomorphisms in the reverse direction. Remember, the direction gets reversed between algebra and geometry always. So those are what are finite type morphisms, those are what are morphisms of algebraic K schemes, okay? And this you can also say that each one has a structure morphism. Spec A goes to spec K and all that glues nicely. So X goes to spec K, Y goes to spec K, and then in the reverse direction, a commutative triangle, okay? So this is the category of spaces for which we are going to set up this homology theory called Chow groups. So it's a kind of homology theory. All of you have met homology theories, different kinds, or cohomology theories in different contexts. Those are all important for this course also. And so we are going to set up this Chow homology theory for these things. So considering this is the kind of scheme we will deal with all the time, a scheme will by default mean an algebraic scheme, and morphism will always mean algebraic morphism. All other kinds of schemes will not normally occur in these lectures. When they do occur, I'll point it out that this is not an algebraic scheme, okay, this is something else. And a special kind of scheme is a variety. A variety is a scheme that is integral, that means reduced and irreducible, in particular non-empty. Okay. So if it was an affine scheme spec A, such a thing is a variety exactly when A is an integral domain. Okay. So usually when you look at textbooks like Hartshorne or Mumford or whatever, standard textbooks, you will find definition of variety to include that it is separated over the base. So here we cannot assume our varieties to be separated for good reason. We will see in examples why you need non-separated things, because you also want Chow groups of non-separated algebraic schemes. And then you need enough cycles in them, and those will come from non-separated varieties. So non-separated varieties have to be there. So all kinds of things that you are used to doing with schemes, I will mean being done over K. So when I take product of schemes, that will be over spec K. And when I talk of affine and projective spaces, that mean affine and projective spaces over K, and so on. Yeah. So I'm going to change the slide. Any questions on this slide? Okay, let's move. So what does this Chow homology do? It starts with one such scheme and makes from it a graded abelian group, Z graded. That's called the total Chow group. And its various components are called nth Chow group, depending on what n is. Now this is 0 on the negative side, and it is also 0 beyond dimension. Okay. However, it's convenient to keep our index in Z so that we don't have to all the time bother about saying this greater than 0, that greater than 0, because automatically things will vanish and the statement will be true without you all the time having to say something. In particular, we'll have to subtract those indices sometimes, and then we can do it without any trouble. Okay. Now, all of it is 0 if and only if it's the empty scheme. And so to make it consistent with this line, we can put the dimension to be minus infinity. Adjoin this extra number to your natural numbers called minus infinity, or integers called minus infinity. Now what happens for a field? Whenever we set up a homology theory, this is a very interesting question, basic question. What is the homology of a point? So here's the answer. For a base field, the 0th one is Z, and all the others are 0. This is like your singular homology of a one-point space in this respect. And what happens in the top dimension? This is another thing that we ask. So now pay attention, because here is a little departure from the kind of homology theories you might have seen. I am not saying that X is compact. In algebraic geometry, the analog of compact will be, it will be proper or spec K, complete. Whether it is so or whether it is not, the top Chow homology is going to be Z for a variety. Whenever I have an irreducible reduced variety of a certain dimension, its top Chow homology is going to be Z. Whether that variety is a projective variety, so compact, or an affine variety, non-compact, whatever. Dimension 0, they are the same, but otherwise they are not compact in positive dimension. So the top homology, top Chow homology, is generated by the irreducible components. It's free abelian group on those. Okay. Now this association to X you are going to attach its nth homology is a functor, but to talk about functor I have to tell you with respect to what morphisms, because I have told you my objects are algebraic schemes, morphisms are all over K. So this is not a functor in some unrestricted manner that take any morphism of algebraic schemes, and then you have certain graded homomorphism of the Chow groups. No, that doesn't happen. But at least it is a functor with respect to isomorphism. So if I take an isomorphism of x with y, then it will induce an isomorphism from a n x to a n y. Okay? In a functorial manner. To identity isomorphism, it will attach the identity homomorphism. To composite, it will associate composite. Okay? So this is a functor with respect to all isomorphisms to start with. If that's not so, then we won't even look at it, because always we want to be able to deal with isomorphisms. And in the old style mathematics, they would say isomorphism shouldn't change anything. In the new style mathematics, you will say that an isomorphism will induce an isomorphism on whatever it is. Okay? Things have a lot of automorphisms. They are very important in mathematics. All of Galois theory is about automorphisms. All of Euclidean geometry is about automorphisms. Something is congruent to something if there is an automorphism of the plane taking the first figure to the second. So automorphisms are very important, and at the very least, the Chow groups are well behaved with respect to automorphisms or all isomorphisms. There are other functorial properties which are very important, and my lectures are devoted to two of those functorial properties, other more advanced properties. Now, let's look at an algebraic scheme in some detail so that you have a mental picture of what you are seeing. So you see, when we talk of Euclidean space, okay, do you see the empty Euclidean space, or do you see it populated by the figures of interest? There are circles and triangles and lines. And so it's good to see your Euclidean space not as empty but as populated by the things you are interested in. After all, that's what you are bothered about. And so the automorphisms of the Euclidean space are taking one figure to another. They are then called congruent and whatnot. Okay? So just as you populate your Euclidean space by the things of interest, including functions which live on it. Okay? What are the most basic functions which live on a Euclidean space, by the way? Those are the wave functions, or e to the power I x dot y for some fixed y. Okay? And you try to express everything by integrating it in terms of these. Okay? This is the subject of Fourier analysis or harmonic analysis. Okay, I have enough time for such asides right now. Later on it will get hectic. So similarly, for an algebraic scheme, you want to see it populated, not empty. So you want to see your algebraic scheme populated by all its subvarieties, and more by its algebraic subschemes also, and so on. Okay. So in terms of points, this is well provided in scheme theory, because every variety has a generic point, as you know. In every variety, there is a point which is dense in that variety, and it's a unique point, whether the variety is separated or not. There is a unique point which is dense in it. And so all those points are points of my algebraic scheme X. And so all those different figures are already present there if you think scheme theoretically, because the points are not just k-valued points or closed points, but all these other points which are generic points of different closed subvarieties. Because there is this simple 1-1 correspondence, and the correspondence goes like this. So first of all, let's look at what I have written. Each variety has a unique point, which is dense in that variety, that's a generic point. The local ring at that generic point is a field, and that's called the rational function field of that variety. And Fulton's book, which is our main textbook, calls it rational functions on V. That's why this R there. And probably he wants to reserve K, because he does not want our next week workshop to have to invent another notation for K. He's very thoughtful of him. So therefore, this notation he has kept R for your convenience, and K will be used, has been reserved for Srinivas's lectures. And so let's call it R often, but sometimes I'll call it this curly K. Now if spec A is a non-empty affine open subscheme of a variety V, then A is an integral domain, and then this is simply the fraction field. This is what it means in terms of your commutative algebra. That in terms of commutative algebra, if this is a domain which corresponds to an affine variety, because it's a domain, 0 is a prime ideal. And that 0 prime ideal defines a point of spec A which is the generic point. And there, the fraction field A upon B, all such ratios where B is non-zero, that is the ring there. Okay? Now, if I take any point which is not necessarily a closed point and take its closure, okay, and I have to make it a scheme, so give it the reduced induced subscheme structure. Okay? So take any closure, give it this structure, then that's a variety. Conversely, given any variety, it has a generic point. So there is a 1-1 correspondence between points in the scheme, algebraic scheme, and closed subvarieties. Now, closed subvarieties have different dimensions. How does that dimension reflect into this? We will see. But first of all, this is clear to you. This is a bijection between the set of all points of a scheme and the set of all closed subvarieties. And then, if I want to be able to describe this function field purely in terms of this point, then what do? So I simply take the germ, the ring of whatever you call it, germs of regular functions at x, small x, in all of big X, and go model the maximal ideal there. So we are still on the subject of closed subvarieties and the generic points. So I asked you how to recover that field purely from that point, and how to know the dimension of the resulting variety. So the transcendence degree of that field is exactly the dimension of V. Okay? What is transcendence degree? Transcendence degree means how many independent functions you have on it. Functions among which there is no algebraic relationship at all. Like in linear algebra, you ask dimension of vector space. How many independent vectors are there? Means no linear relationship. Linear relationships are all that you have in a vector space. Now you are in a ring, there are polynomial relationships possible. So independent means no polynomial relationships possible. So how many such independent things you can have on the maximum? That's dimension, right? There's justice in that being dimension. Indeed, it is dimension as defined by, say, this nested increasing or decreasing sequence of irreducible closed subsets. Various definitions will give that. That's crude dimension when you do algebra. So that turns out to be this transcendence degree. This is the kind of statements which you have learnt in your basic course in algebraic geometry, and these are the occasions where you can make a mental note in case you don't remember the proof, that to at your convenience once again have a quick look at the proof. Okay. So therefore, considering each point therefore has some kind of transcendence dimension, which is dimension of its closure, there are different kinds of points in X. It's not just closed points and generic point and all others. Each one has a kind of dimension. And so I can make X as a union of these different kinds of points, disjoint union. And then this is where the transcendence degree is n. Okay? And then X will be the disjoint union of all these Xn's. So back and forth, this is the set of n-dimensional closed subvarieties. I'll use this same Xn sometimes for such points, sometimes for closed subvarieties. Now if I have closed subscheme, and you'll notice that this sentence really doesn't use the subscheme structure of Y, it could be reduced for all you know. Then a point is either in X or is in X minus Y. Therefore I have a disjoint union. Transcendence degree is not going to change because the residue field is not going to change. Regard that as a point of Y and take the residue field as a point of Y, that's going to be its residue field as a point of X. Check. So this becomes a disjoint union. On the other hand, there are these inclusions. So what does this inclusion do? It keeps the point as it is, of course, but what in terms of closed subvarieties? It takes a variety in Y, which is a closed subvariety, but such a thing is already closed in X, so it just goes to itself. What about the other way? Now you may have closed subvariety of this open set U. It may not be closed in X. So you have to take its closure in X and give it the reduced induced scheme structure. And that will produce V bar. And what will be V bar intersection U? That will be back to V. Now Fulton has a very nice notation which avoids introducing a separate notation for generic points of varieties when you are not using that generic point, but when all that you are going to do is to use the stock of O at that generic point. And that is this notation. So this will be denoted by this. Otherwise you have to start writing let x be the generic point of V and consider this instead of that, you'll straight away say, look at OXV. So now we are ready for algebraic cycles. We are ready for business. Very good. So I want to talk a bit about cycles in a context which you know. So it is well known in history, and I am not that old, so my memory of what happened about 100 years ago is very faint. But you know, all this homology, cohomology, whatnot, actually came from algebraic cycles. Algebraic varieties were what they were first studying in the 18th century, 19th century, and 20th century, of course. They were studying these varieties and they wanted to understand them. And people like Riemann and Poincaré and whatnot were trying to formulate very general concepts to understand these varieties and how they intersect. And that's the title of this workshop, Intersection Theory. And so they invented the subject of topology because certain properties appeared to be of a certain special kind. And so homology, cohomology, etc. actually came out of algebraic geometry. And well, anyway, so there was this notion of cycles, and homology really is generated by cycles. So you want to know what are the primitive cycles. By adding those, subtracting those, you make other cycles. So there are two notions. One is, what are cycles? What are the cycles? And second thing is, when are two cycles equivalent? So you have to answer both these questions. I'll come to the second question, but let me first focus on the first question. So what are the cycles? And the simple answer which people thought in those days was, well, they had recently realized things like manifolds, though formal definition came only in 1912 by Hermann Weyl, who was then 26 years old, and he defined what's a Riemann surface for the first time and defined manifolds by the same idea. And that's a sheaf theoretic definition, was made more precise by Chevalier in his book Lie Groups 1. That's also sheaf theoretic definition, and then sheaves were defined 5 years later, so people didn't understand this sheaf theoretic definition. In between that, the gluing definition became popular, that's also important. Anyway, so in those days they talked about closed submanifold. You know what's a closed submanifold? It's not just topologically closed, or they talked of closed manifold. A closed manifold doesn't have any boundary. As against that, there are manifolds with boundary. Okay? Now to keep things simple, so you can use Z coefficients, let's think of oriented manifolds. And all of you know what's an oriented manifold. You can tell right from left. And when you have an oriented manifold with boundary, its boundary also acquires an orientation. Because you want to know what's a right-handed tetrad on the boundary. How to make a right-handed tetrad on the boundary? Keep the first vector of the tetrad as an inward pointing normal vector. Okay, because it's on the boundary, there is something like inside of the boundary. So keep the first vector pointing in. There are different conventions. Some others keep the first vector pointing out, or some others apply this to the last vector rather than first, etc. And then a tetrad in which the first vector is pointing inwards, and therefore the n-1 others. If that is right-handed, those remaining n-1 vectors are a right-handed basis for the boundary. This is how the boundary gets an orientation. So I have manifolds, closed manifolds, as cycles in a larger manifold. Take a larger oriented manifold, closed oriented manifolds are cycles. And when are two cycles equivalent? Well, the boundary is equivalent to 0. That's the idea. And a boundary may have multiple components. So when I said cycles are closed manifolds, I mean connected closed manifolds. Boundary may be disconnected, and in that case you take the sum of those components and put it equal to 0. What about reverse orientation? Give a minus sign. So geometrically putting a minus sign is reversing the orientation.
Cycles are formal linear combinations.
Cycles are formal linear combinations, finite formal linear combinations, but they are of fundamental cycles which come from closed oriented manifolds, connected closed oriented manifolds. I am not writing all this down, This is to give you motivation for what's going to follow. But I'm going to test your knowledge of this now with an example. Okay? So I have this real line, R. I give it an orientation. This is positive orientation. Give me a zero cycle. Well, any point is a zero cycle. Give me a one cycle, a one-dimensional, closed, connected, oriented submanifold. What is that? All of it. Okay? All of it. There is only one. While points there are many. Now let's take this point and let's take this point. This is P, this is Q. And now let's take this oriented manifold, which is the interval I. I is the interval PQ. So what is the boundary of I? So because the inward pointing vector is this way, there it will point out, it's going to produce plus P minus Q. I have written this square box to show that I am treating it as a cycle rather than just a point there or submanifold there. So this is the boundary of this. So this I am going to put to be equal to 0. So any point is going to be equivalent to any point, but something even more terrible is going to happen. I take this point P and I take this half line. And what's the boundary of this half line? P. And therefore actually P is equivalent to 0. So finally the homology theory which comes out of this is going to tell you that H1R is equal to Z generated by R. Okay? And H0R equal to 0. Because any point, and after all these are linear combinations of point is equivalent to 0 because it's the boundary of something. Okay? And so this homology theory is called BM. So in the BM homology theory, this is the answer. Okay? You must have seen on your homology theories various indices always. H et al. Or H Durham and whatnot. H singular, H check, there is some, yeah? So this is the BM homology theory, okay? Alright. Goes very far. Now, so another example I want to test your understanding. I just showed you. Okay, now, let's take a cylinder. Tell me what is BM homology of this cylinder. So this of the cylinder, let's call this cylinder C and H1 BMC and H2 BMC. After all, we have discussion hour in the afternoon, so think about it in your spare time and we'll talk about it then. Now let's come back to this. Okay, so that's the kind of geometric thinking analogy keep in mind while learning the definition of Chow groups in the first place. So we begin with the free abelian group Znx over Xn. This Xn, recall, was the set of all closed subvarieties of dimension n inside X. And the generator corresponding to a subvariety V is written by the square bracket, a notation which we already used there. And a general cycle is a finite formal sum. Okay? Where these are integers. You have already seen minus signs coming up in P, equivalent to Q and whatnot. Now, let's look at how it behaves with respect to open subsets. If I am open subset, then this partition tells me that the free abelian group over a set, which is the Ristrian union of two subsets, is the direct sum of those two free abelian groups in a natural way. And so there is a projection on each. So I am more interested in this projection. So this projection will work. You want to look at it geometrically, what happens if I have variety here and it has this class of this variety, no, cycle of this variety. I will not yet talk of classes. So this cycle maps to this cycle of this intersection. Okay? And if that is already in Y, it goes to 0. And if I have two, one is a subset of another, well, this u prime is now going to play the role of x, and the set of points in u prime is a disjoint union of the set of points in u and the set of points in u prime minus u. So you have this kind of prediction again. And this data makes it a sheaf. This is very obvious that this is a sheaf if you think in terms of points like xn. Okay? If you want to think in terms of varieties, and I stick to writing it in terms of varieties in some preprint which I referred to, then you have to take closure and intersect, but the thinking is the same. Okay? Bookkeeping becomes easier with these xn's, something which I didn't know a few months ago. So I want to emphasize this word cycle. So after we have these equivalences and we go modulo them, and I have not yet introduced them, the cycles become class. Because a class of different cycles which are equivalent to each other, that's a class. Before that, they are cycle. Notation, the same. So sometimes you will get confused. Is it a cycle or is it a class? Because our major effort is going to be that some operations that we do with cycles are well defined with respect to classes. And cycles and classes have the same notation. So there is something called proof by notation. So very short proofs are possible, but we won't give those, and we'll give the longer proofs. Okay. All right. So yeah, I must tell you, don't be distracted by all this light entertainment I try to provide along with the slides, but focus on this. Yeah. Shut your ears resolutely to all jokes. Just remove all your sense of humor. So with great seriousness, you keep staring at this. Yeah. Make sure you don't laugh. Now you started laughing. How will you learn then? I don't know. So, any questions on this? None. You see, I have great time control because I know how many slides I am going to show, and each one is carrying a number. So I can afford to tell you something more, or I cannot, this I know. Alright, so should I go ahead? Anand, Sudarshan, now I am worried. No questions. Okay. Now we come to the heart of the matter, because this equivalence of cycles is going to be defined in terms of order of vanishing. So we want to talk of order of vanishing of functions. Now where do you encounter this order of vanishing first? For real functions, in doing real calculus, there is no such thing. You know, you should know this. There is no such thing. You first encounter this when you do analytic functions. And the first time you do analytic functions is when you do complex analysis. Real analytic functions are not introduced to young people. Why this is so, I don't know. But maybe, yeah, some good reason, maybe none. Anyway, so you first encounter analytic functions, means functions which are given by a convergent power series. Those are analytic functions. Like sine, cos, etc., etc. Newton refused to think of any other functions. Or rather, he was forced to think of all those other functions very reluctantly. He used the terminology functions of geometry, means analytic functions, and functions of mechanics, means the function which will describe the position of Newton. Now, Newton was in the habit of walking around in Trinity College corridor, I suppose, and then he will stop, and he didn't have beard, but he had a wig, so he will pull his wig. You know, those of us who have beard have a simple way of thinking, but I suppose. And then he'll stop, and then, then he'll walk again, yeah. But if it was an analytic function, and if of time, and if it is 0 for some interval, such a function is identically 0, right? So Newton's position is not described by an analytic function. So he was forced to go beyond analytic functions, and those he called functions of mechanics. Other mathematicians who were not interested in mechanics stuck to functions of geometry for a very long time, till they were also forced to move off it. That's a separate story, the story of functional analysis and Lebesgue integration and whatnot, that we will talk in some other workshop. Very fascinating story. Okay, so we first meet these analytic functions power series, and then it has an order of vanishing. You know what's the order of that function at 0? Order of vanishing at the point 0. It's not value 0. And that is 0, 1, 2, or some natural number, and that is defined like this. Is your function divisible by z to the power n? Then it has a 0 of order at least n. So take the biggest n such that it is divisible by z to the power n. If it is divisible by all z to the power n's, then such a function has to be identically 0. Okay? This is a property of complex analytic functions. It is not shared by, say, real C infinity functions. So that is how you define the order of vanishing. It belongs to this ideal minus this ideal. And once you define this order, it becomes additive. That you can quickly see because such an f, its power series starts with z, some a n z to the power n plus larger terms. And then when you multiply these two things, bm z to the power m plus larger terms, a and bm are non-zero, their product is non-zero. So the order of vanishing adds. So this also happens in discrete valuation rings. In any discrete valuation ring, the maximal ideal is principal. And so given any non-zero element, similarly you can ask what divides and what is the biggest one it divides, and that is the order. And then once you define it for a minus 0, because it is additive, because of this property, you have well-defined order of vanishing on k. You call it order of a minus order of b. Order of a upon b equal to order of a minus order of b. But the answer can be negative now. Okay? You say that it has a pole. Such a thing has a pole. And that you call the order of the pole if it is negative. Meaning that positive part of that after removing sign is the order of pole. This valuation on discrete valuation rings has another fantastic property which is very foundational in number theory. That property is, what will it give when you add? You know, instead of multiplying, if you add two power series, how much does it vanish? And then there is an equality. After all, the leading coefficients might cancel each other. So the order of its 0 is greater than or equal to the minimum of the two orders of zeros. This property is very important in number theory, and this property is not something that we are going to consider in these lectures. This property won't be satisfied by the generalizations that we will think of. So you won't call this valuation, simply call it order. So now let's move from discrete valuation rings to arbitrary one-dimensional Noetherian local domains. This is the spot at which you have to know a bit of algebraic geometry, because in complex analysis you will never take this step. Or okay, in some advanced complex analysis you might, where you think of analytics varieties, but this has to do with singularities. So let's look at one-dimensional case. So let's look at something singular. This is a curve in two-dimensional space, and it has coordinates x and y, and this curve is given by y square equal to x square into x plus 1. Are you familiar with this curve? You know, the Greeks knew this, and they actually named their first letter of their alphabet after this curve. You know, this curve is called alpha curve. Alpha in Greek means the first one. Okay? Omega means the last one. And so this is the first curve you consider when you think of singularities, and because of its importance, the first alphabet, when they invented writing after some time, they named the first alphabet after this curve, so it's called alpha. Okay? Now, on this point is singular, and given a function, you want to know how much it vanishes there. I am going to give you a function, you tell me how it vanishes there. Take this function, y equal to 0. How much does it vanish at this point? Any guess? Yeah? What's the guess? How much does it vanish at this point? And now people thought of the following simple idea. You just move it slightly. Oh, it vanishes twice. And those 2 points have come together here. This idea is called moving lemma. Okay? So tremendously moving idea, and But we are not going to talk about it. I'm going to straight give you a definition of order without any such moving things around. But this moving will motivate it for you. So you want to tell how much a function vanishes here, even though the ring here is not a discrete valuation ring. And for that, a simple algebraic generalization. In the discussion hour, I'll ask you to implement this definition for this curve and tell me how much something vanishes. And in particular, my question is going to be, take the function x plus y upon x minus y. What's the order at this point? Call it P0. What's the order at P0 of this function? And the answer to this is going to reveal something strange. This order is going to be 0. But this function is not regular at that point. So when things are singular, strange things happen. Something may have order of vanishing 0, but that doesn't make it a regular function there. It will still be a meromorphic function. So I want you to do this simple exercise later. Okay, let's come back here. So if I take a Noetherian local domain of dimension 1, that is what discrete valuation rings are. They are Noetherian local domains of dimension 1. But now I remove the condition, they are DVR. And so the maximal ideal is no more principal. And I still want to say, in the place of this idea, to what power of the maximal ideal it belongs, I want something else. So the idea is Artin local rings. The Artin local rings, as all of you know, are exactly the local rings of finite length. All our rings are, yeah. You have studied Atiyah MacDonald relevant chapter on Artin rings, I take it. So when A is a DVR, we can define the order to be this length. This length is simply the maximum power, minimum power such that A belongs to F to the power n. Okay? So you can define this to be length. So this, yeah, what?
Length, you said the smallest power of maximal ideal.
Yes. Largest power of maximal ideal. Smallest, largest, I might get confused. Okay. So when it's a DVR, you can recast the definition as this length. Okay. The order of vanishing of F is this length. Go modulo z to the power n, for example. So if you go modulo z to the power n, you should be able to give it a filtration, which has n plus 1 steps in it. When you count the length in a filtration, you always name the first one as 0, next one as 1, and then n, which you cannot refine any further. Yeah? So, looks like I see some doubt on the faces of people, which means in the discussion hour we have some business.
Length definition
yes.
for non-DVR is the doubt.
Length definition for any module is you can have a series filtered, which you cannot refine further. Each successive quotient is, so to say, simple. It has no submodule. It's a non-zero thing and has no submodules apart from itself and 0. Such a module is called simple. Yeah? And length is how many such simple steps you have in the graded object. That's called length. So ask these doubts in the discussion hour, and then we will look at examples of things and their lengths.
Or even now, if they have such questions now.
Okay, well, once I reach then this. Because this goes a bit into what I would regard as the background knowledge which you should have, namely Atiyah MacDonald. If you have Atiyah MacDonald level questions, I am not going to slow down in these lectures to answer those, because for that we have time. Please ask them later, and I'll be happy to answer them. In fact, I learned Atiyah MacDonald once, and the day after the exam, I forgot it all. And then when I started learning algebraic geometry, I then started understanding what this meant, and that time it stuck. Okay. Even then, there was one topic in Atiyah MacDonald which never stuck in my head, the primary decomposition related stuff. Okay. And then only after learning some algebraic geometry, I understood that it's the associated primes which are of great importance. and then I restudied primary decomposition and rewrote it for my purpose, and my notes are available to anybody. Okay. So if I have Noetherian local domain of dimension 1, but not necessarily DVR, we define it like this, length. Okay. What happens if A has dimension more than 1? Then this quotient does not have finite length. If it is dimension 1, then this quotient has dimension 0, which means it has finite length. Dimension 0 is equivalent to finite length for Noetherian rings. Now this, therefore, I generalized the definition from DVRs to any one-dimensional Noetherian local domain. We have used the fact that it's a domain in saying that whenever I go modulo something f which is not 0, the quotient is of finite length. If I take, say, kxy modulo xy, and I go modulo x, which is non-zero, then I get the polynomial ring in y, and that's not of finite length. The problem was this x was not 0, but it was a 0 divisor. So later on we'll say that, okay, if you want things which are not integral domains, then be careful to go modulo non-zero divisors. And that's where your associated primes are going to come up. You have to keep away from the associated primes if you want to be a non-zero divisor. Zero divisors is exactly the union of associated primes. Okay, so we have generalized this, but caution, this is not a valuation. So for example, this example shows, if it was a valuation, then something whose value is 0 should be in the ring, but this one is not. And now with this definition, the order is still additive. This is given in the notes. Good exercise for you, that this order is additive. And so because it is additive, now I have well-defined order also on the quotient field. Because it's a domain, one-dimensional Noetherian local domain, it has a fraction field, and I can define the order of A upon B as order of A minus order of B. This is well defined because on A it is additive. So if I may have two ways of writing that ratio, but then this into this is equal to this into this. So then order of this is order of this. But this splits into two terms, this splits into two terms, subtract, and so well defined. Yeah? You understood? This is called hand-weighing proof, and very convenient ones. Okay. They are better than proof by notation, but you really have to write it down to be 100% sure that everything is okay. So here we talked about one-dimensional, and you may start wondering, is this whole theory for one-dimensional schemes, one-dimensional varieties? What do you do in higher dimensions? So it's really not one dimension, but one codimension. In one dimension, the point has one codimension. That is really the significance of that one. Okay. So if I have variety and a one codimensional subvariety, and I take the generic point of that closed subvariety, which is of codimension 1, then the stock of the structure sheaf there, the local ring, is one dimensional. Okay. So you think of an integral domain A and a prime ideal P, and you ask yourself, what is the stock at the point defined by P that's A localized at P? What are the prime ideals in A localized at P? Those are the prime ideals which are contained in P. How many of them are there? That's the codimension. So if I have codimension 1 subvariety of a variety, then the stock at its generic point is a one-dimensional Noetherian local domain. And that is something to which we have defined order of vanishing. So what's going to happen is, if I have regular function on a variety and I have closed subvariety, then I attach an order of vanishing on that closed subvariety. What does it geometrically mean? Geometrically means, first of all, to be 0 okay, let's think of a non-singular situation. For that to be, first of all, for it to be non-zero, it shouldn't be 0 all over this. You are allowed to consider functions which vanish somewhere on this closed subvariety. Yeah? It's not as if your functions are everywhere non-zero on this closed subvariety. They may vanish somewhere. Now you look at the generic point and ask what's the order of vanishing. So that means locally have this little bit of intuition that you go to some kind of a transversal, one-dimensional transversal, and think of this normal direction. This is happening. This you can do at a general point. You want to do it precisely algebraically, you can even do it at the generic point. But if you want to think geometrically, well, there will be points on this closed subvariety where that subvariety is non-singular. This requires things like your field is perfect. But if you are building your intuition, think of a nice situation, complex numbers. So you have closed subvariety, and that closed subvariety has some singularities, but now take some point where it is non-singular. And now think of what's happening in the normal direction. So your given function there, now how much is it vanishing there? In general, there may be some exceptional points where it vanishes more. And then that's the order of vanishing. All this can be done cleanly, neatly in terms of the generic point by simply applying the algebra that we defined. So go to the generic point, take this one-dimensional local ring. The quotient field of this is RV. The residue field is RW. Okay? Even this sentence should be clear to you. Otherwise, go back to the situation where V is spec A. And then that's what you have to do to check this statement anyway. And so, applying this length idea, I have an order function from here to here. And then this is again additive that we saw already, therefore it has a well-defined order function. What's the order of f upon g? The length of go modulo f upon length of go modulo g. Okay? And so any non-zero rational function has a well-defined order of vanishing order along this co-dimension 1 subvariety. So what in your one-dimensional complex analysis, one-dimensional means C1. In C1 you took origin, that is co-dimension 1. In C2 you can take the x-axis or you can take some other curve and ask for the order of vanishing along it. Okay? And so the same terminology is used, order of 0 if it is positive, order of pole if it is negative. Okay, let me ask you. So I have this A2, this is my variety V. And my W is this x-axis. And my function is y minus x square. Okay? My function is y minus x square. And now I want you to tell me what is the order of vanishing along x-axis of the function y minus x square. Everything is happening on A2, which in algebraic terms is spec of kxy. Yeah? Any answer? Somebody answering? 2. Let's be very democratic. It's going for 2. Any advance on 2? Actually, I'll have to consider reduction on 2. Any advance slash what? In auctions, there is no word, no? Okay, all right. Any advance or negative advance on 2, going for 2, going for 2, 2, sold for 2. Now you'll have to justify this in the...
0 is there.
Who answered? Thank you. So, going for 0, that's free now almost. Going for 0, I think it is sold for 0 to this student. You will have to defend your purchase in the discussion hour. Okay. So let's go on. So any other questions? That question was asked by me and not by you. Okay, I can do that. I can start asking questions. Why not? All right, so next slide. So with this order of 0 that I just now talked about, we are ready at last to implement the second point. What are the cycles and when are 2 cycles equivalent? Another way, since we have made it into an abelian group, saying when are 2 equivalent, I really want to say when is their difference 0. This equivalence equivalent to 0 is going to define a subgroup, and the homology is going to be the quotient. So I have to tell you when is something equivalent to 0, and then of course you have to check, yes, see, I have to take the subgroup generated by these basic equivalences and then go modulo it. Okay, so remember here we used an interval which was and took its boundary. Here also we use this half line and took its boundary. What are we going to do for Chow homology? Our cycle is a formal linear combination of the fundamental cycles of closed subvarieties, things like V. Now when is that equivalent to 0? And the idea for that comes from so-called rational functions. So another way of saying that this point is equivalent to this point would have been to consider the function x minus p upon x minus q. This is a meromorphic function. It has a 0 here and a pole there. And therefore, it tells you that p minus q for 0 positive, for pole negative, p minus q is equivalent to 0. Or I simply want to show that p is equivalent to 0. I take x minus p. This is a meromorphic function. It is actually a holomorphic function, and it vanishes exactly once at p. And so p is equivalent to 0. So this equivalence is going to come out of rational functions. And so from a rational functions, we have to have a method to go to a cycle. And then say that that cycle associated to the rational function is equivalent to 0. And how did we do it here? We looked at the pole, we look at the 0. Why is 2p equivalent to 0? Well, you might say, since I want my equivalence to form a group, take the group generated by it. Or I could have simply taken the function x minus p square. It vanishes to the order 2 at p. And that therefore will give me 2p. Okay? So I should use cycles which come out of rational functions by looking at where it is 0, that's positive, where it has a pole, that's negative, what coefficient, order of vanishing, which is why we did all this order of vanishing up to now. So now we are going to implement it. So let's begin with a variety, and you will see this method has an obvious restriction, and we'll have to do one more thing to expand it. So let's take a variety of dimension n, and let's take a rational function in it. Now, any such rational function, and this is something which you know from your Hartshorne chapter 1, think of the affine case when in doubt. In the affine situation, your variety is spec A, and your rational function is f upon g, where f and g are non-zero rational functions. So it's f and g are non-zero elements of that domain A. So take f upon g. Where is it regular? Well, f equal to 0 is a certain locus, g equal to 0 is a certain locus. Throw them out. Rest of the places, it's a regular function, non-zero regular function. Okay? Where does a non-zero function vanish on a variety? So, well, perhaps it vanishes nowhere, but wherever it vanishes, you guys have heard of Krill's principal ideal theorem? No? It tells you that where it vanishes, it defines a codimension 1 subvariety. It's a union of such codimension 1 subvarieties. And this vanishing locus is a closed set in your Zariski topology, and your thing is Noetherian. So there are only these finitely many codimension 1 closed subvarieties where f vanishes, right? And the same thing for g. So if you leave these out, and some of them may be innocent after all. Some of those points may be innocent, some of them cancellations might have taken place. We are not in UFD that you cancel and put it in the lowest form. This is not possible or arbitrary ring. So perhaps we are doing an overkill, we are throwing out some innocent points also. Don't worry about that. At the most, they are finitely many, is what I am saying. Even after killing some innocent people, it's like I didn't commit too many murders of criminals, because the total murders I committed are only 100. So, okay, wrong example, terrible, no? Makes a very bad impression. Anyway, all this is imaginary. Yeah? Now, I was reading statements given by police. Anyway, now, So there are only finite many closed subvarieties where this happens. And for each one of those subvarieties where it is either 0 or polar or none perhaps, you have an integer, well-defined integer. That integer is well-defined by the additivity. And so I define an n-1 cycle like this. Because all of these wi's, which are components of its zeros of the numerator and zeros of the denominator, are codimension 1. So I get this cycle. It's a formal finite sum. Sum is finite, was explained here, finitely many of codimension 1 closed subvarieties. And that is called the Weyl divisor of this rational function R. Now, if you read Fulton, you will see a very complicated notation, which I have kept simple for these lectures. So, he will write it as square bracket of div R. So, from a rational function, first one associates something called Cartier divisor, and then to the Cartier divisor one associates a Weyl divisor, and then that is what. But I bypass the Cartier divisor altogether. Not every Cartier divisor is of the form divisor of R anyway. So directly to a rational function, I have told you what Weyl divisor. So this tells you certain cycles arise from rational functions. And those are the ones I am going to put at 0. But there is one big deficiency in all this. If my variety is n-dimensional, this only tells you what to put at 0 in n-1 cycles, not in anything else. So I'll need to do something else if I want to generalize this to all dimensions. Okay? After all, V is going to have Chow groups in 0, 1, 2, 3, all the way up to dimension n. And so how do I deal with that? That I have to tell you next. But any questions on this one?
Should we usually take varieties to be non-singular in codimension?
Yeah, Harshun will. And he will take perfect base fields and he will achieve that. Okay. He has algebraically closed fields often.
That is perhaps best to be ignored for the moment.
No. See, this variety has this codimension 1 thing.
It's a bad point.
It's a bad point.
You insist on having such a...
Yes, I insist on having these examples. So I cannot restrict myself to the kind of Harshun situation. See, what happens is, once you take a perfect field, or algebraically closed field, which we have here, a variety by itself becomes generically non-singular smooth. By itself. It becomes smooth over the base. By itself. Okay?
The divisors should be also...
But the ambient variety is not smooth there, generically. So this is the difference. Here, this is the point. It's smooth. We are in algebraically closed situation. Point is... This point is a k-rational point anyway, so it is smooth. Okay, whatever field, this point is smooth over the base. See, I should use a terminology which distinguishes between smooth and non-singular and whatnot. Regular and smooth is safe terminology. This non-singular is kind of thing you talk about or algebraically closed fields perhaps. Anyway, let's not go into such distinction. Take your base field to be algebraically closed. Okay? So this point, there's nothing wrong with the point. It's just a point. But this curve is singular there. So the point is generically smooth, but the curve is not smooth. Okay. Thank you, Dipendra. So Dipendra has followed my request for slowing down questions. Yeah, any other questions? So let's go on. So remember, the lesson we have to take from this before I go to the next is, I wanted when one cycle is equivalent to another, or the same as when is some cycle equivalent to 0. Then I want to go modulo that. And that I have given the answer based on what we did in our examples. Rational function, 0, pole. So take the cycle defined by zeros minus poles of a rational function and put that to be equivalent to 0. That cycle defined as zeros minus poles of a rational function is called the Weyl divisor of that rational function. So this you have often done in your study of holomorphic complex analysis, whatever. You have talked of zeros and poles of your monomorphic functions, and you have taken the zeros minus the poles, and these combinations do occur in your complex analysis. For example, what will be the integral? What will be the integral x f prime x, or since in complex analysis you like z, fz, integral of this? It will give you the zeros minus the poles by actually performing the addition. Moreover, using that C is an additive group. If you only do this, it counts the number of zeros minus the number of poles. So this whole idea, zeros minus poles, is very natural. It occurs repeatedly everywhere. Here we are converting it into a cycle. Write a cycle of where it's 0, write a cycle where it's pole, subtract. Give it weightage appropriately by the order of the 0 or order of pole, and that's called Weyl divisor. So this Weyl divisor idea must have been very ancient, but Weyl made it precise in this context perhaps. Or perhaps somebody else named it after Weyl. After all, the name Chow groups was given by Chevalier. Okay.
There is the older notion of a class group. Class group.
Yes.
Same notion.
For
Rational equivalence.
yes, but for these various notions, linear equivalence, rational equivalence, we will discuss those. So, okay. Under good circumstances, the divisor class group, as it is called, the Weyl divisors correspond to Cartier divisors for the kind of situations which, for example, Hartshorne will stick to. But we cannot afford to stick to those. Okay. Alright, so we have introduced the idea of a Weyl divisor and we want to go modulo those with the problem that the Weyl divisors are only in dimension v minus 1. What about other dimensions? And the answer is this. So now if I have any scheme and any algebraic cycle, I want to say when it is rationally equivalent to 0. I am telling you the answer. The answer goes like this. You will need a variety of dimension 1 more than that n. And then if I take a rational function on that, it will produce a cycle of the correct dimension. But how many such varieties will be there? The number of such varieties. Okay? And so there may be a number of such varieties, there may be non-vanishing rational functions on them, and you take their Weyl divisors and you add them up, and if that becomes alpha, then you say alpha is rationally equivalent to 0, and the name for that is rat. And if you smell a rat in this, I'll talk about it. So this is a subgroup, and two cycles are said to be rationally equivalent, alpha equivalent to 0. If alpha minus beta is not the divisor of a rational function on the variety, no, because the dimension may be wrong, but is the sum of Weyl divisors on various sub-varieties of one dimension extra than the dimension of alpha. And then you say it is equivalent to 0. And this quotient group is the Chow group, is denoted by AN. Okay? And then for this, you have to check the properties on slide 1.2. So now I have run through all my predicted 10 slides for this talk, and I have 15 minutes. Great. Okay? So, why this rational equivalence? I kind of pulled this rational equivalence out of a hat, basically. Okay? So, needs better justification, rational equivalence. And a better justification is given on the last 6 slides, A.1 to A.6, which come after this 1.10, then 2.2 lecture, 6 point whatever, 6.10 last lecture, and then A.1 up to A.6 additional material. So there it is proved, the following thing is proved. So there one takes the approach of functoriality. What is the natural property you want these Chow groups to have? You want them to be functorial with respect to proper morphisms in a certain way, which I'll explain in the next lecture or two. You want them to be functorial with respect to flat pullbacks in a certain way. And and of course they have to be functorial with respect to all isomorphisms that we already said. Then the Chow groups have to be generated by cycles. After all, these Chow groups have something to do with the geometry of the situation. And so the submanifolds or the varieties, closed subvarieties are going to produce the cycles. So the group of cycles is as it is. And the push forward under proper morphisms, pull back under flat morphisms on the cycles are completely algebrogeometrically defined. There is no reference to any Chow group or anything in that. And once you put in all these properties, there is just one extra property you have to put in, and that extra property is this. If I take the projective line P1, it has at least 3 k rational points, right? What are the 3 k rational points on the projective line? It may have more after all, but it has at least 3 k rational points. 0, 1 and infinity, right? There are at least 3 points there, okay? So for what k these are the only k rational points? Correct. There are no other k rational points there. It has plenty of close points. How many close points does it have over F2? Infinitely, absolutely. What's the proof? It's the same proof that the number of primes is infinite. Euclid gave that proof. Okay? Alright. How many prime ideals does a polynomial ring have? Okay, if they only finitely when you multiply them all together and add one. Okay? Right? So there are these points. So you put in the demand that 0, the 0 point, should be equivalent to the 1 point or the infinity point. On P1, these 2 points should be regarded as equivalent. Now, you might ask, why do you want to go modulo anything at all? After all, aren't we studying algebraic geometry where we are interested in possible subvarieties? Then why do you want to identify them? Keep them all as it is. Let's not have the Chow groups. Just stick to Zn. You see what is wrong. You know, this is the philosophy of mathematics. It's systematic forgetting. Mathematics is all about systematic forgetting. Systematic forgetting is called functor. There's too much information and you want to cut it down to something manageable. So topological space is something too complicated. Convert it into fundamental group. You have forgotten a lot because there are many different spaces, even they are not homeomorphic to each other, but they are the same fundamental group. So you have forgotten a lot. But the fundamental group is handleable. And so that only came about because you decided to identify different loops which were homotopic. So keeping the homotopy class, forgetting things is one way of cutting down things to something manageable. Should one do it? Now that's another question. What if you want that extra information? Can you put it in some kind of an appendix or some kind of a higher version of things where these things are still there and the equivalences between equivalences are still there in yet another higher thing which you draw upon when needed, and so on and on and on. That kind of things leads to infinity categories. So the whole idea of categorical functors, the usual ones, is to forget a whole lot. Forgetful functor. You see, there is something called forgetful functor, but all interesting functors are forgetful in that sense. Okay? You convert one thing into another, but not faithfully, otherwise you have not gained anything. Whenever you make a map of the earth, there is some joke about map of the earth. Which is the best map of the earth? Well, that's the one that's there in front of us, right? The earth. Everything absolutely faithfully represented with correct distances, positions, no mistake. The earth itself. Identity map. Yeah? Identity map is the best map, but it's also the most useless map. Because you really want to forget all kinds of useless data to keep the main things like the road connects to this one and you want to forget the color of the asphalt there and so on. You really, in everything in pond, you have to forget most of it and focus on something like some character forgot everything except the eye of a parrot or some such thing, okay? Forget everything else. So, you decide to identify one point of P1 to another. How justified is this identifying one point of P1 to another? Well, actually it's a very good idea because there are many things that you do with P1, like line bundles and whatnot, devices associated with line bundles. For many perspectives, this identification simplifies things and is not too destructive. You can go to the other extreme and say that, well, identify everything with everything and have 0 as your answer for Chow groups. That's again totally useless. So there has to be some measure of forgetting with which you produce something whose final test is in how useful it is. So I told you that a functorial approach to Chow groups would be to put simply these conditions, that it should be functorial with respect to all isomorphisms, it should be functorial with respect to the cycles on proper push forwards, flat pullbacks, and one point on P1, k-rational point, should be equivalent to another k-rational point on P1. And then the universal search theory, of course you can go modulo more, but if this is all that you go modulo, then this is naturally isomorphic to Chow homology theory. This is what is proved on those last pages. And the test of usefulness of Chow homology is what you are going to see in the coming 2 weeks, where Chow groups will be powerfully used for all kinds of things like Riemann-Roch theorem, for example, showing that this is something which works. What if you can think of another idea of equivalence? Well, you are welcome to, and it might be very useful in doing something else. So there are many different homology theories which people toy with, but this is a very simple one because of these functorial properties.